This is example number 1 for Helmholtz vortex theorem. In this particular example, we have a spinning tube. So this pipe over here is spinning at the rate, okay? And then the flow is incompressible flow, and the velocity field acting within this tube is given by this expression. We have a couple items that we asked for. The first thing we are asking, the problem asks for, is to tell what the streamline functions are. Okay, can we sketch the streamlines? So we do the streamlines with the stream functions. And so we know that streamlines are given by this expression, where ds is for cylindrical coordinates. This is what we get. Remember that this can also be written as k. This is also equal to k. This is in the k, that's the z direction is k. So this is in general, so I express this, my velocity field also. I like to do it like this, where I express all my thetas in one direction, all my z's in the other direction, and r's in this direction. In this case, I didn't have any r component, as you can see here. So that's why there's nothing there. Then the next thing we want to do is we want to take S cross V. Okay, so we want to take the cross product. Cross product is given by this equation right here. And this whole thing, if I simplify this, I'll get this expression. Okay, but we have done this in the past, so I'm simplifying. I am actually trying to move a little bit faster on this aspect, but you can pause and you can take notes on this. Okay, so now the only possible way this can be 0 is each one of these individual terms is 0. If this is 0, if this is 0, and if this is 0. Okay, why? Because these components can never be 0, and they're orthogonal to each other, and they're independent coordinate systems. So if I want to ensure this is 0, the coefficients of this unit vectors have to be 0. Okay, so let's start. Let's start with easy. Let's say that we know this is the same as k. Okay, so from here we find that RA dr is equal to 0. That's your first expression. Your second expression tells you E theta. Let's go to E theta, the coefficient of E theta. So I took this one. Let's take this term now. It says 1 minus r squared a squared dr has to be 0. But then if I expand this, I can find dr minus dr r squared over a squared. Now if I just manipulate mathematically, this is dr minus r over a dr r over a. Now note that this is equal to 0 because of this guy right here, right? So this is gone, and this all has to be 0. And so from here we find that dr has to be 0. So if I take the integral on both sides, I can show that r is equal to a constant. Okay, so that's the value that I get. So I use these equations. Now let's go to your last equation, that is this equation right here, and let's see what we can do with that. So the first equation from ER now says that 1 minus r squared a squared r d theta minus r a dz, all of this has to be 0. So in other words, r theta 1 minus r over a squared has to equal to r a dz. So I could go ahead and integrate on both sides. If I do that, I find this gives you r theta 1 minus r squared, squared a squared raz, and you're going to have a constant. Okay, so now I can bring this on this side and watch this. So I can write this whole thing like this: r minus r cubed a squared theta minus r a z equal to a constant. Okay, because they are constants, this is the first, this was the first equation that I got, right? This was a constant, and this is the second equation I got, it's a constant. That means that my first streamline function says r is equal to phi is equal to r, okay, and then second equation says that phi2 is going to be r squared r minus r cubed a squared theta minus r a z. Okay, so it's going to vary with r. Okay, and now what happens if, to understand what's really going on here, we have to understand what happens if I give any value of r. So let's say if r is equal to a, what happens if r is equal to a over 2, let's say for an example. So if I say r is equal to a, I find that phi is equal to, psi is equal to a, and I will find that this will give me 0, so this gives me psi 2 will give me minus z, right? This is this will give me a squared, so you have a minus a, this is 0. If this is r over 2, I would get psi 1 will be a over 2, and psi 2 then will be 3/8 a theta minus z divided by 2. Okay, so what you can really see in this problem is that for any given values of r, your streamlines actually have constant values. That's what you're getting, right? This is constant, this is constant. This also gives you a constant. So your streamline functions then basically what they're doing is they're doing the following. I have plotted this more or less here. So if you would, let me redraw this thing all over again. So what you're going to have here is, I want you to think the streamline functions are kind of constant, but they're coming along this tube, okay, surface of this tube. So where it's actually going straight like this, and on the other side, now we are on the other side of the tube, okay, and it's doing something like this. And now you're coming back on the front side, you're going back to the opposite side, and you're coming back on the front side, and it looks like spirals, okay, but you're really moving in constant values of theta. You can see that I have a value of theta is constant, okay, this theta is given, that's constant, going at this constant theta is going around this tube at a distance r. So whatever the distance r I set, if it's going the streamline here and the streamline there will be slightly different, as you can see. And then they are moving along my z-axis. So this is how the streamline functions really work and they look like. The second question you asked is to sketch and derive an equation for a vortex line. Now, if I want to know the vortex lines, the equation for vortex lines is nothing else than this. It's very similar, it's just this is equal to 0. So now what we will do is we go ahead and find the, so we know that omega is equal to the curl of B. So to find that, we can easily just use 1 over r and ER R d theta EZ partial of R partial of theta partial of Z 0 R squared A 1 minus R squared A squared. Okay, and this whole thing, after you evaluate it, gives you the following two terms: A squared plus EZ times 2 over A. Okay, so this is what you're getting. And I want you to know that in this particular case, instead of only having a purely Z direction, you also have a theta direction. And that has to do a lot with the force in which this is actually rotating. Okay, but so we have this. Now we take another cross product. And that cross product will say now omega. That would give you ER E theta EZ dr R d theta dz 0 to R A squared 2 over A has to be 0. So after you do all this, you find that ER is equal to 2RA d theta minus 2RA squared dz minus E theta 2 over A dr plus EZ 2RA squared dr is all equal to 0. So again, we do all of this individually, right? So this has to be 0, this has to be 0. Let's see what happens. So if I go to EZ, if I go to E theta now first, I find that 2 over A dr has to be 0. So in other words, the integral of 2AR is equal to integral of 0. So that gives you R is equal to a constant. Okay, so we know that. Now if I go to the second term, I go to the ER term, you can show that 2 times R A d theta minus 2R A squared dz has to be 0. Then from here you find that d theta is basically equal to dz over A. From here, if I integrate both sides, you find that z is equal to theta is equal to z A plus constant. So then from here, what you can find is that your vortex lines, this is R. Then this another value will be R. This is going to be theta minus z over A. Okay, then what you have, and so these are your constant values, and you can see again that for different values of R, right, if R is equal to A, for R is equal to R A over 2, then these are just constant values, okay? So these equations are spirals, but different from this, they're different slope from your streamline functions, but they're still spirals with constant R as we got before, okay? And we know that this has to be a constant, this has to be a constant, this is a value. Okay, it's not varying, it's just a constant. So we found that. The next question that we are asked for is, are the vortex lines convected with the fluid? So how do we know if they're convected with the fluid? We know they're convected with the fluid if Helmholtz theorem applies. Okay. Now, one of the consequences of that theorem basically states that this has to equal to this v. So when we do this, so let's go ahead and do this, and let's work on this side first. I know that this side is going to equal to partial of omega respect to time plus v dot gradient times the velocity. This term is 0 because it's not time dependent, okay, independent from time. So now we can do, on this part here, we can do a little bit of mathematics here. And we find that this gives you d omega dz is equal to 1 over a partial of omega respect to theta plus 1 minus r squared a squared partial of this respect to z, and your z is not a this is not a function of z. As you can see, the streamlines are only a function of r and r theta, but omega is not, and we found that here. Let me find omega. It's right here, right? This is a function of r. This is a function of, this is a constant value. Okay, so this is a constant value. This is a function of r. There's no z here. So therefore, since there's no z there, this term goes to 0. And you're only left with this term. And this term gives you 1 over a 2r a squared partial of e z respect to theta. This gives you minus 2r a cubed er. Remember, you have to take into considerations when you do this that you have a theta term here. Okay, so so when I did this, so this is what your omega is right here. This is all your omega. Let's take that, bring it over there. Let me just show you what I did. This is your omega, right? This is your omega, but don't forget that when I'm taking the partial of theta, right, I have to use the chain rule. So this will be partial of omega respect to theta with this term, but then you also have of 2RA squared times E theta, and then you also have 2 times RA squared partial of E theta over theta. This term goes to 0, but it's not a function of theta. So when you see here, this term remains, this term goes to 0 because this is a constant. This term remains, and that's where this term comes from. Okay? So now we found what was the left-hand side. We found the left-hand side. Let's work with the right-hand side. The right-hand side now is given by the following equation. Okay? So we evaluate the right-hand side, and this will give you 2 times r a squared theta plus 2a ez dot er partial of r plus e theta 1r partial of theta plus EZ partial of Z multiplied by V. Okay, so when you do the whole thing, you find this is equal to 2a squared partial of V respect to theta plus 2 over a partial of V respect to theta. And if you go back to your equation at the beginning, you find that your velocity is not a function of Z, right? So this is not a function of Z, so all of this actually goes to 0. I'll show you right here. Okay. So you know that the velocity is this. This was given in the problem. So this is not a function of Z. So this goes to 0. I'm only left with this term. And again, this will be partial of V respect to theta would be partial of RA over theta E theta plus, to use the chain rule, R over A partial of E theta over D theta. This is minus ER. So when I plug this back inside here and I simplify, I have this term. I find this gives me minus 2R A cubed ER. You can see I got exactly the same thing here. So I can say that since my left-hand side is actually equal to my right-hand side, then because these are the same, then the vortex lines, I can say the vortex lines are convected with the fluid. I convected with the fluid. Okay. So this basically concludes example number 1 for Helmholtz vortex theorem.